Good morning again to all of you, my students, and today I will deliver my lecture number 2. So let's start. Today I will do some results. First, note down that if a semigroup S has the property that AS is equal to S is equal to SA for every A belongs to S, then S is a group. That is, for every AB belongs to S, there exists XY belongs to S such that AX is equal to B and YA is equal to B. So if a semigroup S has this extra property, that is AS is equal to S is equal to SA for every A belongs to S, then this semigroup forms a group. But this I left you as an assignment for all of you, my students, that you have to prove that if semigroup S has this property, then how it becomes a group, isn't it? How it becomes a group? Because to form a group, this semigroup needs two more properties. That is the existence of an identity element in a semigroup, in a structure, and every element must possess a unique inverse. So these two properties you have to prove using this, isn't it? So if a semigroup S has this property, then S forms a group. We will use this result in our upcoming result. So what does it mean? AS is equal to S is equal to A. So obvious, it means that is for every AB belongs to S, there exists some XY belongs to S such that AX is equal to B and YA is equal to B. It means this. Now the definition. If G is a group, then is a semigroup. If G is a group, then G union 0 is a semigroup, and of course it is a semigroup with 0. And such a semigroup is called a zero group or group with 0. And it is known as zero group or group with 0. Correct? Now the first result of chapter 1, that is proposition 1.1.1 on page number 4. A semigroup with 0 is a zero group if and only if for every A belongs to S minus 0, AS is equal to S is equal to SA. So we have to prove that a semigroup with 0 is a 0 group if and only if for every A belongs to S minus 0, AS is equal to S is equal to SA. So when such type of results are to be proved, that is implies, for example statement P implies, statement Q, then what is the approach? Approach is that we assume that statement P is true and we prove statement Q assuming statement P is true, and then we will prove the converse. Conversely that statement Q is true and we prove using Q statement true, we prove statement P is true. So this is the way to prove. So we have to go with one way, and after that we have to do the converse. Okay, let's start. So proof. Let's assume that let S be a 0 group, that is S is equal to G union 0, where G is a group. Now what is our claim? Our claim is that AS is equal to S is equal to SA. Correct? We have to prove this. So since G is a group, therefore AG is equal to G is equal to GA for every A belongs to G, and G is what? S minus 0. Is it true or not? So since G is a group, so we have this AG is equal to G is equal to GA. Now calculate AS. AS will be what? AG union 0. Because S is what? G union 0. So AS will be what? AG union 0. And AG is what? G union 0. And G union 0 is what? S. So AS is equal to S. Similarly, SA will be what? S. So in this way, SA is equal to S is equal to, so SA is equal to S is equal to AS for every A belongs to S minus 0. Because A belongs to G, so G is what equal to S minus 0. Is it clear? Now this part is trivial. Now see the converse part. Converse part is somewhat interesting. Now let's see how to prove the converse. Please note down. Converse. Conversely, let AS is equal to S is equal to SA. This we have for every A belongs to S minus V. Right? Now let G is equal to S minus 0. Then think what we have to prove. In order to prove S as a 0 group, that is S is equal to G union 0, what we have to prove? We have to prove that G is a group. Correct? So claim, what is our claim? Now our claim is claim is G is a group. Correct? But before proving G is a group, we have first thing I have to tell you that what this condition implies. That set is non-empty or empty. What does this condition imply? It implies that G has more than two elements, isn't it? From this condition straight away. Because I already told you that for every, if this condition holds, it means what? For every A, B belongs to S, there exists some X, Y belongs to S such that AX is equal to B and YA is equal to B. It means that of course it has more than two elements. So since G is equal to, you just write this condition as 1. So from condition 1, it implies that G has more than two elements. So G is non-empty set. Correct? Also, G follows associativity. Correct? Because G is equal to what? S minus 0. And S is what? Semigroup. And elements of semigroup follow the associativity. So when G is equal to S minus 0, elements of G also follow associativity. So to prove a group, what we have to do? We have to prove three more properties. We have to prove that it is closed, closure law. We have to prove existence of identity. We have to prove existence of inverse. Correct? So let us get ready. G is not closed. Is it clear? With respect to the operation. That is, there exists A, B belongs to G such that A, B is equal to what? What should come? If you are on contrary, if you are assuming that G is not closed, it means that there is some A, B belongs to G such that A, B does not belong to G, isn't it? So A, B does not belong to G means what? What should come here? A's operation B, what should come? 0. Because see, in G there is no 0. G is S minus 0. So if A, B is equal to 0, it means that G is not closed. Correct? So let us contrary that there exists some A, B belongs to G such that A, B is equal to 0. Now, S square is equal to S. It can be written as S into S, correct? It could be written as S A. It could be written as B S. Because we have condition. We have condition that this we have. Remember, we have this condition S A is equal to S is equal to A S for every A belongs to B S minus 0. This we have. So from this condition we can write S as SA, S as BS, where A and B are the members of course G. So it will be what? S A B into S, and this is what? S into 0 into S, and this is what? 0. So S square is 0. Yeah, you can write here, of course, A, B. Yeah, A, B are the members of G, of course, we have written already. So S will be SA and it is contained in S square and it is 0. And this is contradiction because S is equal to 0. It's a contradiction. We have already said that G has more than 2 elements, and also S, it's not possible if S is 0. It's not possible. From this condition, it's obvious that it's not possible that S is only equal to 0. Isn't it? So which is the contradiction? So it means what? So it implies that G is closed. Now what is left? What is left? That is existence of identity in G and existence of inverse of each element, isn't it? And I told you that what is the alternative of these two conditions? That is, if we prove now, in order to prove G, so far what we have, G is a semigroup. You can write, so G is a semigroup. Now in order to prove G is a group, we have to prove that AG is equal to G is equal to GA for every A belongs to G. Correct? So this is the alternative condition which I left as an assignment for you. So if we prove this, then this group. And now see from the condition 1, it implies that for every A, B belongs to G S minus 0, there exists X, Y belonging to S such that AX is equal to B and YA is equal to B. See, from this condition, it implies this or not? X is equal to B and Y is equal to B. A and B are the members of G here, S minus 0. But think about this. Think about X and Y. X and Y belongs to G or not? Question is that. See, here X and Y think that can it be 0? No, it can't be 0, because if X and Y are 0, you will get B as a 0, and you have taken B as a non-zero, B as a member of G. So here X and Y cannot be 0. Here X and Y both are non-zero. Otherwise you will get a contradiction. So XY belongs to G. So XY belongs to G, it means what? This is proof. AG is equal to G. Which implies that AG is equal to G is equal to GA for every A belongs to G is equal to S minus 0. Hence G is equal to S minus 0 is a group. So S is equal to G union 0 is 0 group. Hence proved. So in this way we have proved both sides. This is the proof. This is the first result of Howe. Copy it down, and if you don't understand, you can post. If you don't understand any step, you can, all of my students can post in the comments the doubts, then I can answer in the next lecture, in the future lectures. No problem. So okay, we will move to next. I hope all of you understand. Note down that equation. If S and T are semigroups, then the Cartesian product S cross T becomes a semigroup. If we define S comma T into S dash comma T dash is equal to SS dash comma T dash. Isn't it? So we define binary operation like this. You take two pairs S comma T, S dash comma T dash, and this is the binary operation. For our simplicity, we are taking this multiplication like this. Simple product. So it is what S dash comma T dash. So with respect to this binary operation, it forms a semigroup, and it is called direct product of semigroups. So we refer to the semigroup as a direct product of S and T. Now we come to another result, that is theorem 1.13. Theorem 1.1.3